Okay, so as I mentioned at the end of the previous video, what we need to be able to draw Lewis structures of organic compounds is an understanding of the types of compounds that we could be drawing structures for. In other words, we need to know what are the repeating patterns, what sorts of things show up over and over and over again. Once we know those, then it makes drawing the Lewis structures a lot easier. So we're going to be focusing on what's called a functional group. Now, a functional group itself is a group of atoms, or it could be a single atom, in an organic molecule, and it has a particular way that it always reacts. So we would refer to that as a characteristic reactivity. That's how it reacts with other chemicals. So that's a functional group. Now, what's happened is that people have started using the term functional group interchangeably with class of organic compound. So functional groups and classes of organic compounds. So technically, there's a distinction between the two. The functional group is the grouping of atoms within a compound, and it has a particular name. The presence of the functional group places the compound into a particular class. And most of the time, we can use functional groups and classes of organic compounds. We can use those ideas interchangeably. The distinction between the two is not that important for our purposes. So when we talk about functional groups, we're talking about recognizing groupings of atoms within molecules that enable us to assign them to one class or another. So let's start with hydrocarbons, because we've seen some things about hydrocarbons already. And we will start with what are known as aliphatic hydrocarbons. Now, the term aliphatic is a term that's used to distinguish certain kinds of hydrocarbons from others. So if you're a hydrocarbon, you're either an aliphatic hydrocarbon or you're what's called an aromatic hydrocarbon. So aliphatic hydrocarbons are the ones that are not aromatic, and we'll push on that term also a little bit on the next page. So alkanes are hydrocarbons that we've already seen. So an alkane is a hydrocarbon. I'll just say HC for hydrocarbon, so we don't have to draw that out every time or write that out. An alkane is a hydrocarbon with all single bonds. And so typically we refer to those as saturated hydrocarbons. So that's what the term saturated refers to. And we haven't reviewed hybridization yet, so I'll throw this out here as a preview. All the carbons in an alkane are sp3 hybrids. So these are all going to be sp3 carbons. So I'm going to draw a few examples of this using the skeletal format, and you should draw these as well. So some of these we've already drawn. So the first structure that I drew, that's butane again, the 4-carbon chain, and it has no branches coming off of it. There are no groups attached to it. So we could call that unbranched. By contrast, the structure right next to it has a branch coming off of the main chain. So if we think about the main chain as being what I just highlighted, then this carbon here, which I've highlighted in a different color, is a branch off that main chain. So you could have just one branch like I've just drawn, or you could have really long chains with lots of branching and getting lots more complicated molecules like so. Now all these examples we refer to as acyclic. That means that they don't contain rings of atoms. But alkanes can also be what we call cyclic compounds, meaning that they contain rings of atoms. So here's one example. We could call this a 6-membered ring because there's 6 carbon atoms in the structure. Here's a 5-membered ring. And these rings can also have branches coming off of them. So we would call these guys cyclic. So Organic compounds can be acyclic, meaning that they don't contain rings, or cyclic, meaning that there's at least one ring in the structure. Now, an sp3 hybrid carbon atom is going to be attached to four things. It'll have four single bonds stemming from it. And so we have a way to classify sp3 carbon atoms that's going to come in handy when we start looking at certain reactions. So let's take a look at this structure here. This is an example of an alkane, and all of these, therefore, are sp3 hybrid carbon atoms. So let's pick this guy right here. So I've highlighted this one, and we'll classify it. This is what we would call a primary carbon. So this is a primary, which we abbreviate like this, one with a little degree symbol. This is a primary carbon, and the reason for that is that it is bonded to one other carbon. So that's a primary carbon. Let's move over here and look at the carbon atom that I've highlighted in blue. This carbon is directly bonded to two other carbons, one on the left and one on the right. This is called a secondary carbon. So a secondary carbon is bonded directly to two carbons. And now let's take a look at this guy right here that I've highlighted in pink. And you can probably imagine where this is going. The pink carbon is bonded to three other carbons. It's a tertiary carbon. So that's bonded to three carbons. Another type of hydrocarbon is called an alkene. And an alkene contains at least one carbon-carbon double bond. So let's look at a few examples of this. So here's a molecule that has a double bond, a carbon-carbon double bond in it. This one's acyclic. And here's a pair. Now, let's number some carbons in these. So 1, 2, 3, 4, and 5. And let's do the same for the other structure. Okay, so what we see here is that numbering from left to right between carbons 2 and 3 is a double bond in both of these structures. So you might think, well, these are the same, but they're not the same molecule. Now the reason for that is the following. Let's imagine a line like so in each of the structures that goes through the double bond itself. In the structure on the left, carbon 1 and carbons 4 and 5, so you have two different groups here. So you have this group and this group. Those groups are on opposite sides of the double bond, as suggested by that highlighted yellow line that we drew initially. So because they're on opposite sides, we call this a transalkene, as opposed to the other example, where the two groups, so these are the two groupings attached to the carbons in the double bond, those two groups are on the same side of the double bond. So we would call that a cisalkene. And by groups, I just mean groups of atoms. So you can have transalkenes and cisalkenes, and you can also have alkenes that are involved in rings. So over on the right are some examples of what we call terpenes. Terpenes are natural products that contain alkenes. Now, a natural product is something that's biosynthesized in nature. So it's produced naturally by something like a plant or a sponge or an algae or a fungi or something like that. And a lot of these compounds have properties that enable us to use them for medicines and for other things, other purposes. For example, limonene, which is one of the structures shown here, that's the major component of orange oil, and then people actually use this as a cleaning product, among other things. So terpenes are natural products that contain alkenes. So what we can see with the structure of limonene is that limonene has an alkene as part of the ring. So alkenes, just like alkanes, can be either acyclic or cyclic. Alkynes, we saw an example of an alkyne in the previous video. An alkyne is a hydrocarbon that contains at least one carbon-carbon triple bond. And so the structure that we saw is 2-butyne. And let me give you another example. The simplest molecule that you can have that contains a carbon-carbon triple bond is this one. Now this one actually has two names. Many, many molecules have two names. One of its names is acetylene. That's what we call a common name. Its other name is ethyne. Ethyne is what we refer to as a systematic or an IUPAC, IUPAC name. So systematic just means that the name you come up with based on following a system of rules. A common name, by contrast, is one that's been in use for so long that it's a commonly accepted name for the compound. So you could call this compound either acetylene or ethyne, and everyone's going to know what you're talking about. You're going to be learning the systematic or IUPAC approach because concurrent with this set of notes, I'd like you to be working on the nomenclature packet, the first of two nomenclature packets, and that's going to help you to learn how to name compounds. Okay, over on the right is an example of a more complicated structure that contains the carbon-carbon triple bond. So this we could consider as having the alkyne functional group in it. This molecule is actually the birth control pill. So this is what they call the pill. And it also has other functionality or functional groups within it. So many molecules don't have just one feature or one functional group. They could have more than one. And so some of these areas that we're going to be looking at, these OH groups, and then this particular ring. So these are all other types of functionality or functional groupings that we're going to be looking into shortly. So those are aliphatic hydrocarbons. Remember, aliphatic is a term that just means that they are not aromatic. Now, aromatic hydrocarbons, there's plenty of examples of this, and a compound doesn't have to be a hydrocarbon to be aromatic. So we're going to focus for now on the hydrocarbon versions of these. And the simplest one is this one, which I'm going to draw in the skeletal formula. So it's 6 carbons in a ring with 6 hydrogens. Notice that each of the carbon atoms has 4 bonds. So if we look at this carbon atom here, it has a single bond to hydrogen, a single bond to carbon, and a double bond to another carbon for a total of 4 bonds. This one is called benzene. And so this is the major one that I'd like you to be able to recognize. At this point, and in this semester, we're not going to be able to look at what makes something aromatic. But what I will tell you, because we're going to do this in the second semester, is that an aromatic compound, whether it's a hydrocarbon or not, has an unusual stability associated with it. A second feature, or a second thing about aromatic compounds, is that all aromatic compounds contain rings. So they all contain a cyclic component. However, not all rings are aromatic. So for example, here's benzene. That's a 6-membered ring, so 6 carbons. But here's another 6-membered ring made up of carbons. This is called cyclohexane. So hex meaning 6. Cyclohexane is not aromatic. So benzene is aromatic. Cyclohexane is not aromatic. So in terms of recognizing aromatic compounds, you really just want to focus on benzene. Now there's a whole bunch of others. And so what you're looking for is any molecule that contains the benzene piece as part of its structure. Let me give you a pair of examples of this. So here's benzene with a methyl group attached. This is called toluene. Toluene contains a benzene ring, and so it's aromatic. Now, by the way, as long as we're on the topic of drawing molecules, there's 2 ways you could draw this. You could explicitly write CH3 at the end of that bond that's coming off of the ring to make sure that people understand that that's a methyl group. But even if you don't, this carbon over here in the left structure that I've just highlighted blue, because only 1 bond is shown to that, there must be 3 bonds that are not shown that are to hydrogens. So remember, every bend and every end is a carbon atom. So toluene is an example of an aromatic hydrocarbon, as is this structure, which is called naphthalene, which is nearly impossible to spell. Naphthalene includes that benzene ring piece. So you can safely assign it as an aromatic compound. So what you're looking for to identify an aromatic hydrocarbon is the presence of the benzene ring at this point. Later on in the next semester, we'll get into more detail and we'll get more complicated with this, but for now, that would be great. Now, all of these aromatic compounds and other compounds exhibit a pattern that we call conjugation. Now, conjugation can show up in different ways, but in benzene, it shows up as this alternating double, single, double bond pattern. So let's just make a note of that, because we're going to see this in other places. That the conjugation in benzene is reflected in the alternating single and double bonds. Okay, let's take a look at some other types of compounds. So hydrocarbons have only carbon and hydrogen in them. All other organic molecules are going to include heteroatoms. Remember, a heteroatom is something that's not carbon. So we're going to start with a class of compounds that we're going to see a whole bunch of later on in the semester, and these are called alkyl halides. Now, for a lot of these classes of compounds, we have abbreviations so that we can not have to write out, for example, things like alkyl halide every time. So alkyl halides, that class of compounds, is abbreviated as Rx. Okay, now what do those things mean? R refers to an alkyl group. An alkyl group is a hydrocarbon fragment. So it's a piece of a hydrocarbon. And we've seen this already. For example, a methyl group. A methyl group is a little piece of a hydrocarbon. And so we can call this a methyl group is an example of an alkyl group. And then X is an abbreviation for halogen. So alkyl halides are going to involve halogen atoms attached to sp3 carbons. So let's take a look at some examples. We'll start with a really simple one. So here's a methyl group. And if there were a fourth hydrogen on that, we would have methane. But instead of that fourth hydrogen, we have an iodine. We would call this methyl iodide. Notice that a halogen has 3 lone pairs and a single bond. Here's another example. Now this one has 1, 2, 3 carbons and a bromine. Alkyl halides can also involve rings. So you can have alkyl halides that are part of cyclic structures, like this one. Over on the right are some other alkyl halides. The top one is called dichloromethane, which is also known to the fans as methylene chloride. This is a solvent. And the bottom one is a chlorofluorocarbon. These are the guys that are present in the ozone layer and deplete the ozone layer. So things like this are implicated in the destruction of the ozone layer that surrounds the planet. We can classify alkyl halides in the same manner that we classified sp3 carbons. So classify Rx, alkyl halides, using the same method that we use to classify sp3 carbons. So our classification is going to be based on the carbon that the halogen atom is attached to. Let's look at some examples of this. So I'm going to draw 3 structures. Like so. All right, so let's take each one of these and classify it as either primary, secondary, or tertiary based on the carbon atom that the halogen is attached to in each case. So in the first case on the left, the bromine is attached to the carbon that I've highlighted, and that carbon is attached to 1 carbon. That makes that a primary carbon, and thus this is a primary alkyl halide. Now, if you wanted to be really specific, you could say it's a primary alkyl bromide, but primary alkyl halide is just fine. In the second example, the carbon that has the fluorine on it is attached to 2 carbons. That makes it a secondary carbon, and so this is a secondary alkyl halide. And then finally, in the last example, the chlorine is attached to a carbon that's directly attached to 3 other carbons. Here they are, 1, 2, 3. That makes it a tertiary carbon. And because the chlorine is attached to a tertiary carbon, this structure is a tertiary alkyl halide. Let's take a look at some of the functional groups that contain oxygen. So we're going to look at 2. The first one, which is a very, very common, almost ubiquitous type of compound, is called alcohol. So the abbreviation for alcohol is ROH. So what that means is that an alcohol is an alkyl group plus an OH group, which is referred to as a hydroxyl group. Let's draw some examples of this. Using the skeletal formula, like so. Okay, so first of all, how many carbons are in that structure? If you said 2, you'd be correct. This one is called ethanol, or ethyl alcohol. So this is everyone's favorite alcohol. This is the alcohol that you drink if you drink alcohol. If you go out for drinks, this is what you're having, is ethanol. Eth is the prefix that refers to a 2-carbon unit. So an ethyl group would be a 2-carbon alkyl group. So let's draw some more examples. Here's a cyclic alcohol. So an OH group or a hydroxyl group attached to an alkyl fragment. And then, of course, these structures can get pretty complicated. Lots of branching, and so on. Notice that an oxygen, when it's neutral, is going to have 2 lone pairs and 2 bonds. Some examples of natural products. These two are used in the perfuming industry, are shown to the right. These include not only the alcohol functional group, but they include alkenes as well. So remember, a molecule doesn't have to be limited to just one functional group. It can belong to more than one class. Perhaps a special case of an alcohol would be this one. We can call this an aromatic alcohol or a phenol. And that would just be benzene with an OH group. Now, one thing that you have to be on the lookout for is the following. So here's a different structure. And you might recognize this as one that we drew a little while ago. This is a carboxylic acid. Even though it has an OH group, you have to be careful because this is not an alcohol. So this is a carboxylic acid, not an alcohol. The reason for the distinction is that the hydroxyl group is attached not to an sp3 carbon, but instead, to a carbon that's involved in the carbonyl group. So that takes it out of the alcohol category and puts it into the carboxylic acid category. Now we're going to go ahead and classify alcohols using our same classification system. This is going to be based on the carbon that the OH group is attached to. So if you classify that carbon, then you've classified the alcohol itself. In other words, this is exactly like what we did with alkyl halides. So let's revisit ethanol. And then we can look at a couple of other structures as well. So these guys. Okay, so you identify the carbon that the OH group is attached to in each structure. So on the structure, or in the structure on the left, the carbon that the hydroxyl group is attached to one other carbon, making it a primary carbon. So this is a primary alcohol. So we'll say primary ROH. In the middle example, the OH group is attached to a carbon that's attached to 2 other carbons. So that's a secondary carbon, making this a secondary alcohol. And then you probably know where this is going. In the third example, the carbon that the OH group is attached to 3 other carbons. Thus, it's tertiary, making this a tertiary alcohol. Another type of functional group that contains oxygen is called an ether. The abbreviation for an ether is ROR. So what you have is an alkyl group, an oxygen, and another alkyl group. Let's look at some examples. So here's an oxygen that's flanked by two methyl groups. We would call this dimethyl ether. But the two groups on either side of that oxygen don't necessarily have to be the same. So here's another one. In this case, there's a methyl group on one side of the oxygen and an ethyl group on the other side. So CH2, CH3, the two-carbon hydrocarbon fragment, or the two-carbon alkyl group, is called an ethyl group. We would call this one ethyl methyl ether. Ethers, just like the other compounds that we've been looking at, can be cyclic or acyclic. So here's a cyclic example. The oxygen is part of the ring. So you have 4 carbons and 1 oxygen. So you have a 5-membered ring. This one is called THF. That stands for tetrahydrofuran, which is a common solvent. So that's an example of a cyclic ether. Now, a special example of a cyclic ether is this one. So this is the simplest example of this that we could find, or that we could run across, and this is called an epoxide. So an epoxide is a special example of an ether. It's a 3-membered ring, which means that there are 3 atoms that make up the ring, with 2 carbons and 1 oxygen. So the one that I've just drawn is the simplest version of an epoxide, but you can have some more complicated ones as well, like the structure that I've drawn to the right. And then directly above it, the pre-printed structure is THC, which is the psychoactive component of marijuana. And right through here is the ether functional group in THC. Notice that THC also includes an aromatic alcohol, or a phenol. And finally, an alkene. So a few points before we move along. First of all, you might wonder, why don't you call the double bonds in the benzene ring alkenes? Now, technically they are carbon-carbon double bonds, but they react differently than a regular carbon-carbon double bond that's not involved in the aromatic pattern. And so we're not going to really point those out as being alkenes necessarily. So that's one thing. A second thing, you might be thinking, as we're drawing these skeletal formulas, that you're not really sure what's going on in these structures. So what you want to do as you practice getting used to this is maybe to draw the structures that I've drawn as skeletal formulas, draw them as full Lewis structures. Okay, so it's totally okay to do that. You don't have to use the skeletal formulas, but I'm going to be using them a lot, so you need to be able to know how to interpret them. But as you learn that, you may need to go back and forth between the simplified skeletal format and the full Lewis structure. The third point that I'd like to make is that I've been giving you names of things, of specific molecules. For example, on this page, I told you what THF was and what dimethyl ether was. You don't need to memorize names of things. What you do need to learn is how to name molecules, or certain molecules, and that's what the nomenclature packet is going to be for. But you don't have to know the names of specific molecule examples that I'm giving you. I would give those to you on tests. It's probably not worth your time memorizing that kind of thing.